Hi, and welcome to another video mini lecture about Java compilation. Today we're going to look at the journey that a Java program goes on as it's transformed from source code to bytecode to executable machine code. Let's start off by looking at a simple Java program. It's called hello.java. So this program lives in a class hello, and there's a single main method which creates an integer and then concatenates the string representation of this integer with the string hello. This is all very familiar, simple Java code. Now let's compile this program on the command line using the Java C compiler. And we end up with another file called hello.class. This is the Java bytecode, JVM bytecode, representation of the same program. So we can see the source code of the program as text here. And we can try and do the same for the bytecode version of the program, although it's not really text, it's a binary file. So when we try and generate it and view it as a text file, you see we end up with something that looks quite difficult to understand. What we really need to do if we want to view the bytecode of the program is to disassemble it. I'll do that here using the Java P utility, which is installed as part of the Java SDK. So I'm going to disassemble the code of the hello class. And you can see here, as I scroll up, that the main method of the hello class consists of these bytecode instructions here. The first instruction loads a constant, LDC, and the constant to be loaded is the integer value 1, 2, 3, 4, 5, 6, 7 here. This value is stored into the first local variable slot. And then we go through some library code to construct, well, first of all, to get hold of the system out print stream, store that in the stack, and then to construct a string builder and to append various values to this string builder. First we append constant hello, there's the append, hello argument to append. Then we append the integer value, which we're loading from the local variable. And then we call the toString method on the string builder. And then we call the printline method on the print stream, which was already stored on the stack. And finally, we return. So you can see that 2 or 3 lines of source code instruction six lines to be precise, turn into 24 lines of bytecode instructions. So the bytecode is necessarily simpler and therefore more verbose than the source code. We can run our hello program by invoking the Java virtual machine using the Java command. As expected, it produces the output hello 1, 2, 3, 4, 5, 6, 7. What's happening is that the Java virtual machine is interpreting the bytecode instructions we saw earlier, and for each bytecode instruction executing a predefined sequence of native machine instructions. Now, this machine here is an x86 64-bit machine, which means it executes Intel instructions. We can actually see the precise sequence of Intel instructions, machine instructions, that correspond to every individual bytecode operation. Now, to do this, we have to use some extra flags in our Java virtual machine invocation. You can see them here. We need to unlock diagnostic VM options and print interpreter. But now when we run this, the code executes, but at the same time it prints out this long sequence of native instructions. They're disassembled into assembly language that correspond to each bytecode instruction. What I'm going to do is save this into a file called code.txt, and then we can go look at this at our leisure. Code.txt. So, we're going to have a look at the interpreter template first of all for the load constant instruction. Remember, this was one of the JVM bytecode instructions which was part of the program, the hello program. And you can see that a single bytecode instruction corresponds here to 320 bytes of native machine instructions. And here they are here. So first of all, there's some kind of stack push operations, then some conditional jumps, and some data manipulation operations, and so on. And the template carries on further and further down, and eventually we get to the end. We're not there yet. The end will be a jump. There we go. A jump back to the next instruction. Okay, so each bytecode corresponds to one of these long sequences. Let's have a look at invoke virtual, which remember is a Java method invocation in the bytecode. This is a much longer sequence now, 1000 bytes of x86 64 instructions. And again, you can see it starts off in a similar way, setting up its state, and then doing some checks, and then eventually executing the call. I'm not sure precisely which instructions do that, and at the end we'll see another jump to get back to the next instruction. What we see is that JVM bytecode is compact, but when that's translated into native machine code, it becomes much more verbose.